Hello everyone and welcome to lecture today. So today we're going to be talking about a very interesting idea, which is the idea of limit cycles. And we've already talked about limit cycles in the in-person class. However, we're going to kind of dive a little bit deeper today into the fundamental mathematical understanding of limit cycles. And we're really just going to focus on theorems 2D. However, limit cycles can appear in any number of dimensions for any number of first-order systems, which is why we'll start by just kind of writing down some basic notation here. So specifically, we use our standard system notation for an ND first-order system of differential equations. With a possible initial condition set at T naught. And for a 2D system, we recognize this immediately as xi1 prime is equal to g1 of xi1, xi2, and xi2 prime is equal to some function g2 of xi1, xi2. And all of the ideas in 2D that I'm going to develop and go over can be generalized to 3D and any number of dimensions as well. But when you do that, there are a lot of other things that can possibly go wrong. In 3D, the systems of differential equations can exhibit very complex behavior, such as chaos, which we'll get into a little bit later. So we always want to think along the lines of our linearization process from 2 lectures ago. It's always a good way to start trying to understand things. So let's say we have a point xi star and a point xi, possibly xi of t, the solution to the differential equation on some orbit. You know that we can define the distance vector function h of t as being the difference vector as a function of t from xi star to xi. So in 2D, xi star is x star, y star. And xi is equal to xy. The xi notation is convenient for larger systems, but in general we'll just be talking about x and y in all of the examples today, just because it's a little bit easier to graph and kind of conceptualize. So we know that h, the difference vector, is xi minus xi star, which we can represent in terms of polar coordinates, where r is the radius or the magnitude of h, and r hat is a unit vector, specifically the unit vector cosine of theta, sine of theta. Theta is just the normal angle from the x-axis. I should say the angle from the point, the projection of the x-axis onto this point right here. So this angle theta right here. And as the solution moves around the curve xi of t, theta and r are both functions of t. They're changing as a function of time, or whatever the parameter, the independent variable is. So r and theta are functions of t, which means that we know that the magnitude of h squared is equal to r squared, and we know from polar coordinates this is going to be the same thing as x squared plus y squared. So the goal here is going to be to get a system of differential equations that's related to our original first order system of differential equations, but depends on r and theta instead of x and y. We can actually use this very often to obtain information about how a solution is traveling and a solution is moving in a given region. The first thing we're going to do is differentiate this implicit relationship. And when we do this, we get that 2 times r prime is equal to, and I should be more specific here. This is only x squared plus y squared if x star and y star are 0. It's going to be x minus x star squared plus y minus y star squared. So when we differentiate, we get 2 times x minus x star times x prime plus 2 times y minus y star times y prime and this is sometimes a little bit more convenient to write down in terms of h, where this is going to be 2h1 prime times, or 2h1 times h1 prime plus 2h2 times h2 prime. And if the point that we're expanding about is the origin, obviously this simplifies just to x and y here. But we want to be careful here and make this as general as possible, because this is a very useful method to use if you have a non-zero or non-origin equilibrium point that you want to evaluate, or many other possibilities here. But the idea here is that very quickly we see that we can solve for r prime as h1 over r times h1 prime plus h2 over r times h2 prime, and since h1 is x minus x star, which is r cosine theta, h2 is y minus y star, which is r sine theta, and h1 prime is equal to x prime, and h2 prime is equal to y prime, or g1 of xy, g2 of xy, r prime is going to be equal to cosine of theta times g1 of r cosine theta r sine theta, where we have to plug in for x and y into whatever the function g1 is, the right hand side of the x derivative equation, plus h2 over r, which is sine of theta times g2 of r cosine theta r sine theta. In this differential equation, it looks a little bit more complicated than the differential equation for x, but for many systems, this will provide us with a great deal of simplification. I'll show an example of this in a little bit. But our system is incomplete if we have two first-order systems in Cartesian coordinates for x and y. We're going to have two first-order differential equations for our polar coordinate system, which is essentially what we're doing here. We're just converting the polar coordinates about the point xi star. And so, first we recognize that the angle theta is related to x and y through the tangent function which is just should be other way around, y over x. Which in terms of h is h2 over h1. So again, if we differentiate, we obtain secant squared of theta times theta prime by the chain rule, and by the quotient rule this will be h2 prime times h1 minus h2 times h1 prime divided by h1 prime, or h1 itself squared. Which looks a little bit more complicated until we realize and kind of break down what everything is here. Remember, secant squared is the same thing as 1 over cosine squared. So this equation is the equation we solve for theta prime. Theta prime is equal to cosine squared of theta times h1, which is r cosine of theta times h2 prime minus r sine of theta, which is h2, times h1 prime, all divided by r squared cosine squared of theta, because the denominator is h1 squared. And we see this really cool thing happen where cosine squareds cancel out, and r over r squared is 1 over r, so theta prime is just going to be equal to cosine of theta over r times h2 prime, which is the same thing as g2 of x, or g2 of r cosine theta r sine theta, then minus sine of theta over r times g1, and then r cosine of theta plugged into that, r sine of theta plugged in. you have it, in general, this new system of differential equations is a system of differential equations that describes trajectories of our differential equation relative to some fixed point. But the idea is that typically, we're going to end up using this to kind of characterize really what's going on around a given equilibrium point. And we know how to classify stability versus saddle point versus all of the different classifications in 2D. But in some sense, there's much more behavior that can occur, much more complicated behavior that can occur for nonlinear systems. And this is exactly what we're getting to, which is the concept of a limit cycle. And we're going to see that this idea is very, very important for analyzing these. I guess that the best way of seeing that is probably to consider a specific example. This is a very, very nice example that can be found in the Kelly book. So we'll take, for our system, xi is xy. We'll take xi dot, or xi prime, to be x dot, y dot. Is the function x plus y minus x times x squared plus y squared, and the function negative x plus y minus y times x squared plus y squared. And there are a number of different ways of proving that the only equilibrium point of this system is going to be the origin, 0, 0. But hopefully you can clearly see that we'll at least have one equilibrium point for the system, which is xi star equals 0, 0. And if you go through and use Desmos, say, to plot the null lines of this differential equation, you see very clearly that as long as the asymptotic behavior of each one of these null lines is consistent with this plot, very clearly the only equilibrium point is the origin here. There are different ways of proving this, but I won't go over that right now. The idea, though, is that if you, say, take a second to evaluate the sign of the derivative in each one of these regions, and this is a very important idea in what's going to be to follow, which is the Poincare Bendixson Theorem, after I finish covering this example. And it's related to the idea of invariant regions discussed in the previous lecture. So for any point here, the only possible direction the point can go is in this direction, within this range of angles, because the x prime must be negative, so it must be decreasing, and y prime must also be negative. So the direction of solution here is forced to go in a specific direction by the null lines. Similarly, in this region, x prime is positive, but y prime is negative, which means the solution direction is forced to be in any angle here in the fourth quadrant relative to any one of these points. Likewise here, x prime is positive and y prime is positive. Which leads to any solution having to have a tangent vector that points in this direction right here. And similarly, in this region right here, x prime is negative and y prime is positive, so the solution direction can only point in this range of angles right here. And what's interesting here, though, is that if we kind of move down into this region where the null line has some weird behavior, these directions also have to be preserved. Which means if we go right here, these directions are the directions that have to hold for the solution. If I say go right here to this point right here, these are the directions that have to hold for the solution. If I go right here, these are the directions that have to hold for the solution. And lastly, if I go to this region right here, these are the directions that have to hold for the solution. And so what this is giving us then is it's giving us a fairly clear indication, just the null line picture alone, of what's going to be going on with general solutions. Just by kind of thinking about this picture that I've kind of graphed for you, we almost immediately expect that this is going to be an unstable critical point, but the solution is somehow going to be forced to stay around this critical point right here. And sure enough, we can go through and show this exactly. This is going to be our first big example, very good example of a limit cycle. And we'll prove that this has a limit cycle and why it has a limit cycle before we show any plots of this, to show that we can go through and do this. The Jacobian matrix, first and foremost, will evaluate at this critical point. But if we go through and evaluate the Jacobian matrix of our system, it becomes negative 3x squared minus y squared plus 1, 1 minus 2xy, negative 2xy minus 1, and negative x squared minus 3y squared plus 1. At the one critical point, this matrix we'll call A, and it has a relatively nice form. It is 1, 1, negative 1, 1. And so the trace is 2, and the determinant is also 2. 1 times 1 minus negative 1 times 1. And because both of these are positive, we conclude that the point 0, 0 is an unstable equilibrium point. So we've shown what we suspected from this picture, that 0, 0 is an unstable equilibrium point. And now if we rely on using the work that we did over here in deriving our system in polar coordinates, remember this is the deviation system, the system of differential equations that governs the deviation from any point xi star in polar coordinates centered at that point xi star. This is a very convenient system to use because the system that we've chosen to analyze only has one equilibrium point, and this is at the origin at 0, 0. Oh, and we'll just abbreviate this as R G of R theta, G1 of R theta, G1 of R theta, I don't want to get confused if you have to end up using these equations and plugging into a problem that is not centered at the origin. You can still use everything that we did before. You just have to mind the fact that x's and y's have to be shifted by the critical point itself. So I'll probably go back and plug this in there, over there as well, just to keep the notes consistent. So I want to emphasize that if x star and y star are non-zero, when you plug in for x and y here, you have to make sure that you do this shifting right here, because if x minus x star is equal to r cosine theta, for instance, you have to plug in for x here, x star plus r cosine theta. This is a very important point to make. I just wanted to make sure that I emphasize that. In this problem, it doesn't really matter because x star, y star is 0. But for problems where x star or y star is non-zero, you have to do that correct substitution. So anyway, when we substitute each one of these things in, I'll make a copy of our g function just for reference. And also remember that x is r cosine theta, y is r sine theta. So we'll consider r prime first, and then theta prime. R prime is cosine of theta times r cosine theta plus sine theta minus, and when I plug in here, I get r cubed times cosine of theta. As x is r cosine theta, and x squared plus y squared is just r squared. And this has to be added then to sine of theta times negative r, or r times negative, rather, cosine theta plus sine theta, because x is r cosine theta, y is r sine theta, minus r cubed sine of theta. And it's starting to look a little bit complicated until you realize that you do these multiplications out. You'll get cosine theta times sine theta here times r, which cancels with negative r cosine theta sine theta here. So ultimately this term cancels with this term right here. And for the other term, something really special happens. You get r prime is equal to r times cosine squared theta plus sine squared theta, and this one is going to be negative r cubed cosine squared theta plus sine squared theta, which is 1 and 1. So you get that r prime is equal to r minus r cubed, or r times 1 minus r squared, which is completely decoupled from theta. But simultaneously we do have to solve the theta equation now. And I'll let you go through and verify what the theta differential equation is going to be, but we are going to use it, so I will plug it in here. Sure enough, when we go through and do this, you end up getting that d theta dt, or theta prime, simplifies even more than the r equation does. Simplifies down to negative 1. And so now we have actually a relatively, very straightforward system that we can go through. We can go through and solve. We can solve for r as a function of theta. If you want to go through, this is a separable differential equation for r here as a function of t. So you integrate 1 over r times 1 minus r squared dr. This is going to be equal to the integral of dt. And you can go through and solve for r as a function of t, and likewise theta as a function of t. It's just going to be negative a negative t plus some constant c, which is the initial angle. Likewise, when you integrate this, you'll get that r of t is equal to natural log of r minus 1/2 natural log of 1 minus r squared. This is going to be t plus some constant d. However, and this is very interesting, right? That this is a solvable example, so you can actually go through and check numerical solutions. However, in some sense, this isn't entirely the point. What we want to look at here is how to take this differential equation itself and determine some properties about what's happening with solutions without even going through the solution procedure. I definitely recommend being familiar with and understanding how to go through and and do this for simple examples. However, we really want to get at the main point in all of this, and the idea here is that just using the differential equations here, this new system of differential equations for r and theta, we can say that, well, there's not going to be any equilibrium points because theta is always non-zero, or theta prime is always non-zero. However, there is an r nullcline. The r nullcline is when r prime is equal to 0, which only happens when r equals 0, which is at the point 0, 0, which is an unstable equilibrium point. But r prime is also 0 on the radius, which is when r is equal to +1. And r is always positive, so we don't need to include the negative root of this 1 minus r squared. This r equals 1 is a nice, the circle of radius 1. And what we're seeing is that r prime is equal to 0 for each point on this circle of radius 1. So trajectories that intersect this circle are staying on this circle. The radius is not changing. However, theta is constantly changing, so it's constantly moving around. This is exactly the limit cycle for this problem. And we predicted that without even going through and solving the differential equation for r. And this method will always be able to give you some insight into this idea. So let's go through and take a look at what these limit cycles look like. If we plot this trajectories in the phase plane for t from 0 to 1, sure enough, we see that the solution starts to spiral in, and if we plot the trajectories from 0 to 10, you very strongly see that this limit cycle behavior is appearing exactly on that circle that we predicted using the differential equation. And perhaps the best way of viewing this is to go to the animation. So I opened up our Python code from earlier, and I added the feature into it to produce a bunch of, save a bunch of images to put them into an animation. And this animation looks like the following. So you can very clearly see all of those points evolving with any given initial condition, evolving onto that limit cycle. So this is really cool. This phenomena can be understood in a number of different ways, but primarily there are a couple big theorems that we can use here, and the idea is that it's related to the language introduced before of positively invariant sets and the omega limit sets of a given differential equation orbit. In general, the problem of finding cycles is difficult. In the previous example, we were able to use polar coordinates to find the periodic solution, but it's not always as nice and smooth as that last example. The fundamental result that we can use for general 2D systems is called the Poincare Bendixson Theorem. And for this theorem, we're going to be considering a system of nonlinear differential equations in 2D. And this says the following. So consider star, and I want to make a emphasis that this is for n equals 2 if psi of t comma or psi of t comma eta is a bounded orbit for positive t, and W is its omega limit set that was defined in the last lecture. Then either one of the following is true. W is a cycle or limit cycle, or for each point y in W, the omega limit set of psi of t comma y is a set of one or more equilibrium points. And the proof of this is actually very technical. So much so that it's not in the book. In the book, they give a rough sketch of how to prove it, so you get an idea of why it's true. But the full proof can be found in the text by Hirsch and Small. The reference is fully in the Kelly book. And the main idea is that if you can go through and bound so you use the fact that if you can bound the solution in invariant region, either one of these two things has to be true. So in some sense we already showed with this phase plane diagram right here the basic idea of how you would, in a more advanced way, go through and actually prove this general theorem. And it strongly relies on constructing a positively invariant region surrounding a given region that you're interested in. So let's go through and see how to use this for a slightly more complicated example that's related to the previous problem, but a little bit more complicated than the previous problem. And this example is going to be, we'll consider the derivative of x is x plus y minus x times x squared plus 2y squared, and y prime is negative x plus y minus y times x squared plus 2y squared. A small change, but a change that nonetheless will make the polar form a little bit more cumbersome to use. However, using the differential equation in polar form and the Poincare Bendixson Theorem, you still can go through and get a very nice idea of what's going to happen and show that there has to be a limit cycle for this problem. So this is the main change here. We still have one equilibrium point of our system. And if you go through and do the method that I showed earlier, the differential equation in polar form ends up simplifying down directly to the following. And I'm not going to go through the calculations here. However, it'd be good for you to go through and show just for practice. You get r prime is equal to r minus r cubed times 1 plus sine squared of theta you still do get a relatively nice differential equation for theta. But this now is a coupled nonlinear system of differential equations. But we can still use this, even if we can't go through and directly solve this in the following way. So we note that on the circle, r equals 1/2. R prime is 1/2 minus 1/8 times 1 plus sine squared of theta, will always be the maximum of sine of theta is 1. And because we have a negative sign right here, we want to focus on this maximum, because if we know that sine squared theta is maximum when sine is 1. So then the minimum value of this expression right here is when theta is 0, or is when sine of theta is 1. So then you get 1 plus 1, which is 2 over 8, or 1/4. So the minimum value of r prime on r equals 1/2 is 1/2 minus 1/4, which is positive. And we know that the equilibrium point is an unstable equilibrium point and we've just shown that on r equals 1/2 the radius is always changing positively across it, so the solution is entering into the region outside of this circle, radius r equals 1/2. Likewise, if we look at a slightly larger radius of 1.1, into the same procedure, we'll end up getting that r prime is 1.1 minus 1.331 times 1 plus sine squared of theta, and the maximum value for this is going to be when sine squared of theta is 0, or sine of theta is 0. And so this will be less than or equal to 1.1 minus 1.331, which is negative. And so this is circle radius 1/2. You look at a circle radius 1.1 now, and we're seeing that solutions on this circle that enter into this circle have a negative change in r. And so this region right here, this annular region, is an invariant region, positively invariant region for this system of differential equations, and therefore by the Poincare Bendixson theorem, because there are no equilibrium points inside this region D, by the Poincare Bendixson theorem, there must be a limit cycle. In D. Now, in this example, this invariant annular region has the property that all orbits that intersect it must enter into the region itself. But in some cases, a portion of the boundary may be invariant. So we'll see how to deal with this in a second. However, I do want to show visualization, right, of the solution curves for this example. This is a picture of the annular region described before, this positively invariant region. And if we see a plot of the trajectories here, we can very clearly see why we chose the annular region that we did, because it traps this limit cycle inside of it. And you see very clearly that the solutions that are close to the equilibrium point here at the intersection of the null lines are moving away from the equilibrium point, and the solution for initial conditions that are outside of this annular region are moving in to this this limit cycle, and the limit as t goes to infinity. And so I'm going to go over one more example here of directly applying this theorem, and this has to do with a more complicated example, but also more relevant example towards applications. The previous two problems have been just examples to sort of illustrate where we're going and how we use the theorem. What we're going to consider now is the generalized predator-prey model that we talked about a number of weeks ago in our active learning sessions. So this is specifically the non-dimensionalized generalized predator-prey problem. This is found in the Ends book. This is one of our course texts. So you remember that this was the prey equation for x was a logistic type growth with a predation term that's saturated and the predator growth also depends on the relative ratio of predators to prey. Equation 1 and equation 2. And it's a little bit more convenient to put these in a slightly nicer form for analysis. Simply by bringing them to common denominator and realizing that this first equation is the same thing as 1 minus x times x plus c minus axy divided by x plus c and y prime becomes b times y times x minus y over x is equal to 0. The equilibrium points of this system are a little bit more cumbersome to evaluate. We'll start with equation 2. Oops, and this should not equal 0 in general. So when we set equation 2 equal to 0, we have two possible ways of satisfying this. Y can be equal to 0, or y can be equal to x. And in the case that y is equal to 0, we can satisfy equation 1 being equal to 0 by having x be equal to 1 or x be equal to negative c. Gives us the equilibrium point 1, 0 and the equilibrium point negative c, 0. For the y equals x term, we have a little bit more work. So if y equals x, this numerator is 0, therefore this equation is 0. But then this right here has to be 0 in order to satisfy equation 1. Which means that 1 minus x times x plus c minus axy which is just ax squared left equal to 0 because y is equal to x. And this expression will, oops, I just realized I need to have an x term right here. My x term I wrote on the outside here, but that should be right here. Multiply by this guy. It's important to point out too that x equals 0 is not a possible solution to this. Even though you can factor an x out here, x equals 0 is not a possible solution because of the division by 0 here. And this reduces to y being equal to 0 as well. So this is nice actually because we can factor this entire thing as x times 1 minus x times x plus c minus ax and if we go through, this becomes a quadratic formula for x that solves this term right here being equal to 0. And the exact expression you get is 1 minus c minus a plus or minus the square root of 1 minus c minus a squared plus 4c over 2 are the roots of this equation right here, which satisfy the equilibrium point conditions for equation 1 and equation 2, and therefore we have 2 new critical points, or equilibrium points. The equilibrium point x1, x1, and the equilibrium point x2, x2. x1 is a negative part of the square root, and x2 is a positive version of the square root. So we have 4 total equilibrium points, each one of which can be classified, but we're going to focus on the equilibrium point x2, x2, because this is the equilibrium point that we're interested in the predator-prey model, where the populations are both positive. This equilibrium point lies in the first quadrant. And we can get a nice picture of this just by looking at Desmos plot of the null lines along with the equilibrium points plotted on for any number of values. So let's open that up and take a look at that right now. And this is the Desmos plot of the null lines, where I've also included all of the equilibrium points that we solve for in terms of any general A, B, or C in the problem. And you can see that as we change any one of these values, the equilibrium points in general are going to change. But they change in a way that's predictable. We just solve for the exact values in terms of the parameters for the problems, so we know what each of these is going to be. It's also important to point out that when x is equal to negative c, we have a discontinuity. The same thing when x is equal to 0 here in the function itself. So we have a switching point in the sign of x prime and y prime at both of these. And this can be visualized just by looking at the region where x prime is positive. In this case, the red region right here and the blue region right here is the region where x prime is negative. And likewise, we can do the same thing for y prime as well. But this will be important a little bit later on. So if we take our system and linearize it, specifically we look at the Jacobian matrix at our equilibrium point, our system is I prime is equal to this vector function of our variables, so the Jacobian matrix, as we take the derivatives all the partial derivatives of g becomes the following. 1 minus ay over x plus c plus ay over x plus c squared minus 2 times x and then the y partial derivative of this will be ax over x plus c and the x partial derivative of this becomes b times y squared over x squared, and the y partial derivative of this becomes b minus 2by over x. And so at the equilibrium point that we're interested in is x2, x2, we solved for before. The stability of this critical point will be determined by A, where A is the Jacobian matrix of G at psi star. And this simplifies a little bit. The first term becomes 1 minus ax2 over x2 plus c plus ax2 over x2 plus c squared minus 2 times x2. The y partial derivative of g1 at x2, this term, becomes negative ax2 over x2 plus c, and this term simplifies a lot because x2, when x equals x2, y equals x2, this is just 1, and this term, y equals x, also simplifies to just being negative b. And even though the Jacobian does simplify a little bit, we want to be kind of specific, and we'll look at a specific example for values of a and c just to get some numbers down. So suppose a equals 3/4 and b equals 5 over 100. In which case then x2 will be 1 over 10 times 1 plus the square root of 6 and our a is just the matrix A11, B, A12, negative B. Where A11 is equal to 1 over 25 times 53 over 2 minus 17 square root of 3 over 2, which is approximately equal to 0.22717. And A12 is equal to 1/5 square root of 3 over 2 minus 9 over 2. because this is a 2x2 matrix, we know how to classify the critical points. We look at the trace of A, which is this A11 minus B, the sum of the diagonal components of the matrix, and we look at the determinant of A, which is this times this minus this times this, which simplifies to 2 over 25 times 3 square root of 6 minus 2, which is approximately equal to 0.47. And 87 times B, which is greater than 0. And so the thing that really determines the stability of the system is B. Specifically, if A11 is less than B, this is going to be negative. A11 minus B will be negative, and therefore this equilibrium point will be asymptotically stable. Which means solutions close to it should converge into that point. Remember, this is specifically the point x2, x2. And if B is less than A11, this equilibrium point will be unstable. Because this will mean that the trace is positive. And we can actually, definitively analyze this using the plot from before very, very nicely. So this is the plot from before, and if we consider the fact that in this region x prime is less than 0 and y prime is less than 0, in this region x prime is less than 0 and y prime is greater than 0, in this region x prime is greater than 0 and y prime is greater than 0, and in this region x prime is greater than 0 and y prime is less than 0, as well as in this region right here, x prime is greater than 0, y prime is greater than 0. In this region, y prime is less than 0, and x prime is greater than 0. And we can even look at these regions as well. This quadrant 1 inside quadrant 1 we have a region where the solution is positively invariant. Because if it's negative here, x prime is negative here, and y prime is negative here, solution direction will be like this. X prime is negative here, and y prime is positive right here. The solution direction will be like this. X prime is positive in this region, and y prime is positive in this region, so the solution direction will be like this. And lastly, x prime is positive in this region, y prime is negative in this region. The solution direction will be like this. We can go through and construct a positively invariant region and directly show that this region surrounding this equilibrium point is in fact positively invariant. And what's incredible here is that by the Poincare Bendixson Theorem, we have that, well, if this is asymptotically stable, this critical point is asymptotically stable, there's no problem, because the solutions will go ahead and just converge to this equilibrium point. But in the case of it being unstable, we have that there has to be a limit cycle for this system of differential equations that describe the predator-prey equations. And this gives us exactly rigorous justification for why this is the case. So let's go through and look at the solutions. We'll look at the specific solution for b is equal to 0.3, which means that it's greater than a11. And sure enough, we see the the solutions are all converging down onto that equilibrium point. So this is a very convincing justification of what we just did. And you see the solutions are slowly but surely spiraling down onto that equilibrium point. However, if we slightly change the value of b by just a little bit, so we move it down to 0.15, we see the bifurcation that occurs, and this is the old solution for point 3. Give me 1 second to open up the solution for point 5, and that's right here. The equilibrium point bifurcates and goes from being asymptotically stable to unstable, and thus we get by the Poincare Bendixson Theorem the appearance of this limit cycle. So this is very, very incredible, and what's even more incredible in my mind is the fact that we can definitively understand this mathematically with what's going on here.